Welcome back to Basic Electronics. In this lecture, we will continue with the RL circuit example from the previous lecture. We will then look at an RC circuit with a switch and learn how to obtain currents and voltages in the circuit before and after the switch position changes. We will then look at an RC circuit in the periodic steady state with a square wave input. Okay, let's get started. So this is the solution that we obtain using the conditions that we found for I of t at 0 plus and infinity. At 0 plus, I is 0, and as t tends to infinity, I is 1 ampere. Alright. Now this of course is only part of the story. Why? Because in reality, the source voltage Vs changes at t equal to t1. So therefore this solution is really valid up to t1, that is up to 0.1 second. And we need to work out the rest of the solution, that is the solution for t greater than t1, this interval here. And how do we go about that? We know that as we go from this interval t0 to t1 to this next interval t1 to infinity, the inductor current must remain continuous. That means the value of the inductor current I at t1 minus, that is just before t1, must be the same as the value of I at t1 plus, that is just after t1. For this interval t0 less than t less than t1, this interval here, I of t turns out to be 1 minus e raised to minus t by tau ampere. And this expression describes this part of the solution. And you are of course encouraged to derive this expression. How do you do that? Let I of t be k1 e raised to minus t by tau plus k2, where k1 and k2 are constants to be determined. And now use the conditions that we derived in the last slide, namely I at 0 plus equal to 0 and I at infinity equal to 1 ampere. With those conditions, you can find k1 and k2, and then you will end up with this expression here. And once we have this expression, we can find I at t1 minus, that means I at 0.1 second. All we need to do is replace this t with 0.1 second. This tau, as we saw in the last slide, is also 0.1 second. So we end up with I of t equal to 1 minus e raised to minus 0.1 by 0.1, that is e raised to minus 1. So that turns out to be 0.632 amperes. And I at t1 plus, as we just argued, is the same as I at t1 minus. So therefore I at t1 plus is 0.632 amperes. So that is one condition that we have for I of t in this last interval here. What is the second condition? The second condition is I at infinity. So let us see what that should be. What is the situation at t equal to infinity? Vs is 0 and it has been 0 for a long time. The circuit is in steady state. All quantities, voltages and currents, would have become constant. This current would have become constant, so therefore this V, which is L di dt, would be 0. This voltage is therefore 0. No current flows through R2, and I is simply Vs divided by R1. Since Vs is 0 at t equal to infinity, the current is 0 amperes, like that. Alright, so now we have two conditions, I at t1 plus and I at infinity, and now we can get the complete solution for this last interval here. Let I of t be equal to a e raised to minus t by tau plus b in this interval, that is t greater than t1, and now let us find a and b using these two conditions. It is convenient to rewrite I of t as a prime e raised to minus t1 by tau plus b. We are not really changing this equation. all we are doing is shifting the origin from t equal to 0 to t equal to t1. Alright, let us now use these two conditions. I at t1 plus is 0.632 amperes and I at infinity equal to 0 ampere. At t1 plus we have I equal to 0.632 amperes, so we put 0.632 here, t equal to t1 plus here, so this argument becomes 0 and e raised to 0 is equal to 1, so therefore we get 0.632 equal to a prime plus b. At infinity I is 0, so we put 0 here, and e raised to minus infinity is 0, therefore this first term goes away and we get 0 equal to b. And putting these together we get our final expression for I of t in this last interval t greater than t1, and that is I of t equal to 0.632 e raised to minus t1 divided by tau amperes. And this is what the solution looks like in the final interval t greater than t1. At t1 I is 0.632 amperes and at t equal to infinity it is 0 ampere. So now we have different pieces of the solution available to us, one piece in this interval and one piece in this interval. All we need to do now is to put these together like that. So this is our complete solution for I of t. The SQL file for this particular simulation is available to you, given here, and you can play with it. For example, you can change R2 from 40 ohms to 20 ohms and predict first of all what should happen, and then run the simulation and check that your prediction is correct. Here is our next example. It is an RC circuit with a switch that opens at t equal to 0. So the switch has been closed for a long time and opens at t equal to 0, and we are interested in finding this current I as a function of time. Now this situation is very different than what we have been looking at so far, because when this switch opens our circuit changes. Before t equal to 0 we have one circuit, and after t equal to 0 we have another circuit. So let us see how to handle that. Here is the situation for t less than 0, that is when the switch is closed. When the switch is closed we have a short circuit here, assuming the switch is ideal, and therefore this circuit diagram applies. After the switch opens, that is when t is greater than 0, this switch is an open circuit, and therefore this entire branch is not in the circuit anymore, and the circuit reduces to this circuit shown over here. Now this situation for t less than 0 has been there for a long time, so therefore this circuit is in steady state. We can use that fact to find Vc over here, and that capacitor voltage value serves as the bridge between these two situations, because as we know the capacitor voltage must be continuous. So Vc at 0 plus must be equal to Vc at 0 minus. To begin with, let us look at the situation at t equal to 0 minus. That means we are looking at this circuit, and at 0 minus the switch has been closed for a long time, so this circuit is in steady state. What is the meaning of steady state? That means all currents and voltages have become constant. So therefore this voltage Vc has also become constant, and therefore Ic, which is C dV C dt, is equal to 0. So this is an open circuit, and the current path is given by this path here, and that tells us what this current I should be. It is simply 6 volts divided by the total resistance in the circuit, that is 1K plus 5K. So 6 volts divided by 6K, that is 1 milliamp. So we have I at 0 minus equal to 1 milliamp. What about VC at 0 minus? We have seen that this current is 0 at 0 minus, and therefore there is no voltage drop across this resistance, and then this voltage VC is the same as this voltage here, that is I multiplied by 5K, and I is 1 milliamp, so therefore we have 1 milliamp times 5K or 5 volts. So VC at 0 minus is 5 volts. And because the capacitor voltage must be continuous, VC at 0 plus in this circuit must also be 5 volts. So therefore we have VC 0 minus equal to 5 volts and VC 0 plus also equal to 5 volts. And that tells us what I at 0 plus should be. Let us look at this circuit, because now we are talking about t greater than 0. This voltage is 5 volts, and I therefore is 5 volts divided by 5K plus 5K, that is 0.5 milliamps. Alright, now let us find the current I as a function of time for t greater than 0, and let us begin by assuming that I of t has this form: a e raised to minus t by tau plus b. So we need to determine three things: tau, the time constant, and then these constants a and b. What is the time constant for this circuit? It is RTh times C, where RTh is the Thevenin resistance as seen by the capacitor, and in this case the Thevenin resistance is simply these two resistors in series, so therefore 5K plus 5K or 10K. So the time constant then is 10K times 5 microfarad, that is 50 milliseconds. Alright, what about A and B? To find A and B, we need two conditions on I. We already have one condition here, I at 0 plus equal to 0.5 milliamp. Let us now find I at infinity, and that gives us the second condition. To find I at infinity, let us look at this circuit. What is I here? I is VC divided by 10K. Now as this current flows, the capacitor gets discharged, so that will keep happening until the entire charge on the capacitor is exhausted. So finally we have no charge on the capacitor, VC becomes equal to 0, and therefore I becomes equal to 0. Another way to find I at infinity is to use the fact that the circuit would be in steady state as t tends to infinity, and all quantities, currents and voltages, would have become constant at that time. So therefore this VC would have become constant, and the current IC, which is C dV dt, would be 0. If IC is 0, then of course I is also equal to 0. So now we have two conditions: I at 0 plus equal to 0.5 milliamp and I at infinity equal to 0. And using these two conditions, we can find A and B, and we get this expression finally: I of t equal to 0.5 e raised to minus t by tau milliamps. Here is a plot of I as a function of time, and the current I is in milliamps here. This is 0, and that is 1 milliamp. At 0 minus, I is equal to 1 milliamp, and in fact it has been 1 milliamp for a long time because the switch has been closed for a long time. So therefore the current I has been constant. When the switch opens, the current changes, and at 0 plus, that means just after t equal to 0, we have I is equal to 0.5 milliamp. 0.5 milliamp is right here. So therefore at t equal to 0, there is a discontinuity. Before 0 we have 1 milliamp, and after 0 we have 0.5 milliamp. And subsequently I of t is given by 0.5 e raised to minus t by tau milliamps, and that part of the curve is shown over here. Eventually, of course, as t tends to infinity, this term becomes 0 and I tends to 0, as we see here. Now, how long does the transient last? We expect it to last for 5 time constants. What is the time constant? The time constant is 50 milliseconds. 5 times that is 250 milliseconds. That is 0.25 seconds. Here is 0, here is 0.1 second, 0.2 second, and so on. So 0.25 seconds is here, and we do observe that after 0.25 seconds the current does not change, it becomes constant. Here is the capacitor current as a function of time, and that is also plotted in milliamps. This is 0 and this is minus 0.5 milliamps. What is the situation at 0 minus? At 0 minus, we have this circuit and it is in steady state. Vc is constant and therefore the capacitor current is 0. And that is what we see over here. And it has been 0 for a long time because the switch has been closed for a long time. So that explains this part of the plot. What about 0 plus? After t equal to 0, this circuit comes into picture, and then we have IC equal to minus I. And since I starts off at 0.5 milliamps and goes to 0 eventually, IC starts off at minus 0.5 milliamps and then goes to 0 finally. And notice that there is a discontinuity at t equal to 0. Alright, let us now look at the capacitor voltage. What is Vc at 0 minus? We already looked at that. Vc at 0 minus is 5 volts, and it has been 5 volts for a long time, and that explains this part of the plot. What about t greater than 0? For t greater than 0, we have this circuit, and Vc now is equal to I multiplied by 5k plus 5k, that is 10k multiplied by I. Now I is 0.5 milliamp at 0 plus, and then eventually it goes to 0. So therefore Vc would go from 0.5 milliamps times 10k, that is 5, to 0, like that. And as we would expect, the capacitor voltage is of course continuous. There is no discontinuity at t equal to 0. The SQL file for this particular simulation is given over here, and you can run this simulation and look at all of these variables and also some other variables that you may be interested in. Here is our next example. It is a series RC circuit with R equal to 5k and C equal to 1 microfarad, and the input voltage is a square wave. In this interval, the input voltage is high, that is 10 volts, and in this interval it is low, that is 0 volts, and then it repeats. It is periodic. Let us say that our capacitor is initially uncharged. That means Vc is equal to 0 volts at t equal to 0, as shown over here. And at t equal to 0, the input voltage goes high to 10 volts. As a result of that, the capacitor is going to start charging like that toward 10 volts. But that does not happen, of course, because at this point the input voltage goes back to 0 volts, and now the capacitor starts discharging towards 0. And that discharging process is also not completed because the input voltage once again becomes high. So therefore the capacitor starts charging again. And this process repeats until finally we have a steady state situation. This kind of steady state is called periodic steady state, as opposed to the DC steady state that we have looked at earlier. What happens in the periodic steady state? Let us take this VC as an example. VC starts off at this point. It does change within one period, but then after one period is over, it comes back to the same value where it started. So that is the meaning of periodic steady state. Let us now look at the current waveform. The current is denoted by IC here, the capacitor current. In this first interval, when the input voltage is high, the current is positive, and in fact that is responsible for this increase in the capacitor voltage. In the second interval, the input voltage has gone back to 0 and the current becomes negative as shown over here. And this negative current is responsible for this decrease in VC. So this keeps happening. The current is positive here, positive again, negative again, and so on. And finally, the capacitor current waveform also reaches the periodic steady state. That means within one period there is a change in IC, but after one period is over, the IC value comes back to where it started. Alright, and our problem has to do with finding VC of t and IC of t in the periodic steady state. Let us look at the problem statement now. This is our input voltage waveform. It's a square wave going from 0 to V0 and then back to 0. T1 is the interval in which the input voltage is high, that is V0, and T2 is the interval in which the input voltage is low, that is 0 volts. Alright. So the problem is to find expressions for VC of t, that is the capacitor voltage, and IC of t, the capacitor current, in the periodic steady state. And these expressions will be in terms of R, C, V0, this value, T1 and T2. Here is a schematic diagram showing the capacitor voltage and the capacitor current as a function of time in the periodic steady state. The light blue graph is the input voltage, Vs. During this interval marked by T1, the input voltage is high, equal to V0, and during this interval marked by T2 here, the input voltage is low, that is 0. During the T1 phase, the capacitor voltage rises from V1 to V2, and during the T2 phase, the capacitor voltage decreases from V2 to V1. So within one period, the capacitor voltage comes back to where it started off, namely V1. In the T1 phase, when the capacitor voltage is increasing, we have a positive capacitor current, and in the T2 phase, when the capacitor voltage is decreasing, that means when the capacitor is discharging, we have a negative capacitor current. And the capacitor current is also periodic. Now the maximum value of IC is denoted by I1 over here, and the minimum value is denoted by minus I2. Now this minus sign is introduced to make our algebra easier. So note that this I2 is a positive number, so minus I2 is negative. Our objective is to find expressions for VC of t and IC of t. Let us begin with VC, and we should note first that VC will be represented by two expressions, one expression in this T1 phase and another expression in this T2 phase. Alright, so let us begin with the T1 phase, and in that phase let VC be a e raised to minus t by tau plus b, and we will call that as VC1, where this superscript 1 indicates this T1 phase. So we now need to find A and B. The time constant, of course, in this case is simply R times C. To summarize, we learned how to treat an RC circuit with a switch. We also looked at the salient features of the current and voltage plots for that circuit. We then started with an RC circuit with a square wave input. We looked at the meaning of the term periodic steady state and started analyzing the circuit in that condition. In the next class, we will complete the analysis and also compare the results with plots obtained by circuit simulation. Until then, goodbye.